What if we could travel to another star in days, not centuries? The Alcubierre Warp Drive is a mathematical idea that bends space-time. Today we'll do a deep dive on what stands between theory and interstellar travel, and how AI might be the missing tool to get us there. In 1994, physicist Miguel Alcubierre, while working on his PhD, proposed a fascinating and audacious thought experiment. He devised a solution to Einstein's notoriously complex field equations, the very mathematical framework that describes gravity as the curvature of space-time. His solution described a mechanism for faster-than-light travel that doesn't actually break the cosmic speed limit. The idea is to create a warp bubble of distorted space-time that expands the fabric of space behind a ship and contracts it in front. Imagine you're on a moving walkway at an airport. You are walking at a normal pace, but your effective speed relative to the terminal is much faster. The Alcubierre drive works on a similar principle. The ship itself sits inside a tranquil, isolated region of flat space-time and doesn't locally exceed light speed. It's the bubble of space-time itself that moves, carrying the ship along for the ride at potentially enormous velocities. This is the core of its genius. It moves space around the ship, rather than moving the ship through space. It's elegant math, a beautiful piece of theoretical physics. But translating this mathematical dream into physical reality immediately slammed into two colossal roadblocks. The first was the need for a substance with properties so strange it's dubbed exotic matter. Specifically, matter with a negative energy density. The second was the sheer astronomical energy requirements, which made the concept seem utterly impossible. Let's tackle problem 1. Negative energy density. To create the required space-time curvature, expanding it behind and contracting it in front, the equations demand a region of matter with negative mass, or negative energy. This isn't just a new type of fuel, it's a form of matter that, as far as we know, may not exist in any stable macroscopic form. We don't have a practical source of that. The only places we've ever observed or predicted such an effect are at the quantum scale, like the tiny negative energy regions created between two closely spaced plates by the Casimir effect. These are fleeting, microscopic, and nowhere near the scale needed to wrap a starship. Then there's problem 2. The staggering energy scale. Even if you could create negative energy, Alcubierre's original calculations suggested that creating and sustaining a warp bubble for a small spacecraft would require an amount of energy equivalent to the entire mass energy of a planet like Jupiter. Later refinements brought this down, but the numbers remained astronomical, far beyond anything our civilization can currently harness. It's not a question of building a bigger power plant, it's a demand for energies on a cosmic scale, not exactly buildable. And a third, equally daunting set of questions emerged around stability and causality. Would the bubble be stable, or would the slightest quantum fluctuation cause it to collapse catastrophically? How could you even steer or stop it, given that the front of the bubble is causally disconnected from the ship inside? And perhaps most fundamentally, faster-than-light travel opens a Pandora's box of causality paradoxes, like the ability to travel back in time and violate the principle of cause and effect. For decades, these problems left the warp drive firmly in the realm of science fiction. But now, a new tool has entered the scene, one with the potential to re-examine these impossible problems from a completely new angle. Artificial intelligence. AI isn't magic, but it's a powerful amplifier for human intellect, capable of navigating complexity far beyond our own cognitive limits. For the warp drive problem, it's best to think of AI as 4 complementary tools. 1. Simulation at a massive scale, allowing us to explore the physics in a virtual laboratory. 2. Materials and quantum discovery, searching for the exotic properties we need. 3. Optimization and design search, to refine the theory and reduce its impossible demands. And 4. Autonomous experimental control, to manage the unimaginable complexity of a real-world device. Each of these capabilities, powered by modern AI, could systematically chip away at the monumental barriers that have kept the Alcubierre concept impractical for 30 years. It offers a new path forward, not by changing the laws of physics, but by giving us a powerful enough flashlight to search for loopholes. Let's dive deeper. The physics of a warp drive lives at the messy intersection of general relativity and quantum field theory. The mathematics is monstrously complex. This is where AI can first make its mark, accelerating both symbolic and numeric work. Think of large language models and symbolic AI systems not just as chatbots, but as tireless research assistants. They can be trained to scan decades of physics papers, cross-referencing theories and identifying obscure mathematical techniques. They could propose novel tweaks to the Alcubierre metric itself, or even hunt for entirely alternative spacetime metrics that might achieve the same effect with less, or even zero, negative energy. Beyond theory, AI excels at simulation. New classes of AI models, like neural PDE solvers and differentiable simulators, can explore millions of parameter combinations for different warp bubble geometries. They can vary the shape, thickness, and energy distribution of the bubble, testing for stability and calculating the energy requirements for each configuration. This is a task that would take centuries using conventional supercomputers, but AI can perform this search orders of magnitude faster. Practically, this means an AI could be tasked with a specific goal: find a warp bubble geometry that pushes the requirement for negative energy into tiny, manageable regions, or find a way to replace it entirely with complex, but physically realizable configurations of electromagnetic or quantum fields. These AI simulators can also act as early warning systems, spotting the subtle signs of quantum instabilities that would destroy the bubble, and then proposing alternative field patterns or geometries to stabilize it. The theoretical work is crucial, but physics is an experimental science. We need to find evidence, however small, that these exotic effects can be produced in a lab. Even tiny experimental clues, like creating engineered Casimir cavities that slightly enhance negative energy effects, or designing metamaterials that can mimic the properties of an exotic stress-energy tensor, could be a monumental breakthrough. This is the second area where AI is poised to revolutionize the search. AI is already being used to design novel materials with unique properties and to accelerate the pace of discovery in quantum experiments. An AI could be tasked to design metamaterial lattices, artificial structures with properties not found in nature, that can bend light or other fields in ways that approximate a space-time distortion. It could run millions of simulations to optimize nanoscale geometries to amplify the subtle quantum vacuum effects that produce negative energy. Furthermore, AI can guide the design of quantum simulation experiments, using one controllable quantum system to simulate another, more complex one, allowing us to probe analogues of negative energy physics in a controlled laboratory setting. In short, AI could act as a bridge between pure theory and tangible experiment. It could analyze the theoretical requirements and then search the vast space of possible materials and experimental setups, pointing experimentalists towards the most promising configurations where the required exotic effects might finally become measurable or prove to be stronger than we ever thought possible. Now, let's imagine we succeed. We've found a lower energy metric, and we've built a material that can generate a tiny, localized space-time perturbation. The next challenge is control. Managing such a device would be fiendishly difficult. The system would be inherently unstable, requiring thousands of adjustments per second to maintain the integrity of the bubble. This is far beyond the capability of any human operator. Here, AI's third and fourth roles, optimization and control, become paramount. Reinforcement learning and advanced neural control networks are perfectly suited for this, as they can learn to stabilize complex dynamic systems that humans can't hand-tune. An AI control system could monitor an array of sensors in real time, managing the strength and shape of the containment fields. It would feed this sensor data into stabilizing controllers that anticipate and counteract instabilities before they cascade. Simultaneously, it could run a continuous, distributed optimization process, constantly fine-tuning the system to keep the warp bubble stable while minimizing the colossal energy usage. It would be the autonomous pilot and engineer, all in one. So what does a realistic roadmap look like? This is speculative, but it can be grounded in practical steps. In the short term, over the next 5 to 15 years, we can expect AI to significantly accelerate fundamental research. This is already happening. AI tools will help physicists find lower energy metric variance, propose novel lab experiments to test for quantum vacuum effects, and design the first generation of metamaterials intended to mimic spacetime curvature. In the mid-term, say 15 to 50 years, the goal would be to translate these theoretical and material gains into physical proof. This could involve prototype experiments demonstrating scalable negative energy analogues, or the first controlled spacetime perturbations at microscopic scales. This would be the Kitty Hawk moment for spacetime engineering. Then, in the long term, 50 years and beyond, if, and it's a huge if, the energy scaling problems shrink dramatically and the stability issues are solved, the first engineering prototypes of a propulsion system could begin to appear. Each stage requires fundamental breakthroughs in physics, materials science, and power generation. AI helps accelerate every stage, but it doesn't replace the need for experimental proof and scientific genius. It's critical to remember that AI is a powerful tool for exploration, not a magic wand. It can show us where to dig, but we still have to do the digging. The ultimate success of this venture will depend on parallel advancements in our understanding of quantum gravity and our ability to generate and control immense amounts of energy. And this brings us to some very big caveats. Even if an AI model finds a mathematically perfect low-energy metric, nature might still have a veto. There could be a yet unknown physical law that forbids macroscopic negative energy. Or, creating a warp bubble might generate unpredictable and dangerous side effects, like Hawking radiation that could destroy the ship or anything at its destination. The safety concerns are profound. Manipulating the fabric of space-time, if it's even possible, is not something to be taken lightly. It could have unknown environmental or relativistic consequences that we can't yet foresee. For this reason, any research in this domain must proceed with extreme caution, governed by transparent, international oversight and rigorous ethical review. This is a technology that, if realized, would change humanity forever, and it must be developed with wisdom. AI won't hand us a working warp drive next year, or likely even in the next decade. The challenges remain immense, but for the first time, we have a tool powerful enough to tackle the sheer complexity of the problem. As a tool for discovery, optimization, and control, AI is the best lever we have to rigorously test whether Miguel Alcubierre's beautiful mathematics can one day become humanity's engineering. It represents a shift from a passive, what if, to an active search for how. If you want more deep dives into the physics of interstellar travel, leave a comment, and don't forget to subscribe for more explorations into the future of science and technology.